My name is Yigit. I'm a second-year PhD candidate working with Professor Giacomo Indiveri at the Institute of Neuroinformatics at Zurich. It's a joint institute between University of Zurich and ETH Zurich. Today, I'm going to give an introduction to DYNAP-se 1, which will be followed by Dmitry Zandrikov's live demo, interactive demo with the chip. Then we will continue 2 hour sessions with the simulation. So just a bit of disclaimer, my research topic is not about the DYNAP-se itself. It's mostly on learning algorithms for spiking networks on constrained fabrics, including memory store integration. And if you check the agenda, there will be, as I mentioned, 2 sessions, 1 hour intro plus demo and 2 hours of simulations. So let's start with the introduction to DYNAP-se. So in this nice workshop, we have been hearing about lots of different neuromorphic computing platforms. And I just wanted to start with pointing the origin of the neuromorphic field and the differences between what we are seeing today and the origin of the idea occurred in 80s and 90s. And today, there are several motivations for research and development of neuromorphic. Some of them include developing platforms, computing platforms, high-performance platforms for neuroscientists. There's also a strong market momentum that really shifts the motivation towards an application-driven inference chips. With this very large demand, now almost lots of companies working on the accelerators for neural networks are positioned under this neuromorphic umbrella. But the very original idea came out at 80s, actually came from Carver Mead, Max Delbruck, John Hopfield, and Orf Heyman, just to really understand how to exploit the physics of natural systems, including the silicon, and reproduce the working dynamics of real neurons. And in fact, at the origin, the idea of neuromorphic was deeply rooted in the biology. For example, the very first students of Carver Mead here, the Misha, was a biologist, in fact, who later developed the silicon retina. So at the Zurich, in the Institute of Neuroinformatics, we follow the second approach. We do interdisciplinary basic research with more than 100 people, including experimental and theoretical neuroscientists, engineers that work on analog and digital design, device modeling, nanofabrication, also mathematicians who works on the nonlinear dynamical systems, so on. And we try to use the real physics of the silicon and emerging new memory technologies, including memory stores, to reproduce an efficient implementation of the neural networks on the substrate. And the systems we develop at INI, including DYNAP-se 1, are actually prototypes, but they are designed for really low power computing of the model of neural network computation at distributed scale. And usually what we do is we really try to test our systems, test our networks and devices in real-time complex behavioral tasks using robotic units and simulators. So we follow the approach of understanding by building. This is very similar to the synthetic biology, in fact. The types of chips that we are building are using subthreshold analog circuits because this subthreshold regime can reproduce the biophysics of real neurons. And this is simply because of the fact that the mechanisms of carrier transport in transistors are diffusion. And we are getting the Boltzmann statistics because of that. And we work with exponentials and logarithms, just like ions crossing the ion channels in the neurons. The type of neuromorphic processors that we are building, essentially very large arrays of these massively parallel analog circuits that implement thousands of neurons and synapses. And one important point here is that this is not a number crunching system. This is a really massive dynamical system that works in real time. And the parts of circuits works only when there's an input to the system. So this is an event-based system. But we do use rates to compute. So we work with spikes, and spikes are, as we all know, are very useful. for the communication and reducing the power consumption of this kind of computation, and also to communicate long distances, both across the cores, across the chips, and also across the boards. And it's also an optimal long distance communication protocol that evolution came up with. So we have analog continuous time streaming circuits that does the computation, and when the neuron, after the computation spikes, we send these spikes digitally across long distances, across different cores, chips, even boards. And most of the circuits here are completely passive. So if there is no signal, it's just a leakage current. And despite this is extremely low power, there's no active amplifiers in any of this circuitry. There's no clock. This is mixed signal chip. So there's digital parts, and digital parts are self-clock. They're asynchronous. So this is why these chips are usually operated in the microwatts regime. It depends on your scale, some nanowatts if you optimize a single neuron. But the price you have to pay for this kind of super low power system is imprecision, noise, inhomogeneity in the computation, and they are slow. Basically, they are not using accelerated time. So it's depending on the point of view, this can be a bug or feature. So if you want to implement really high precision ResNet-like big neural networks, this is a bug. But if you want to build something very, very similar to real neurons and test it, how to deal with this noise behavior, these are features. And since we are using these neurons and synapses, the architecture level with the complex dynamics, with adaptation, feedback, and learning, we believe that they are providing resilience and better generalization. So this is really actually a paradigm shift in the computation. We have memory and computation co-localized in the same place. There's no one Neumann bottleneck. There's no bottleneck due to the information communication between processing unit and external memory. There's no time multiplexing either. We put resources on chip, as many as required. And since we are working with spikes and inhibitory feedbacks, almost always the activation in the circuit is really sparse. And there's no clock in the circuit. Everything works, as I said, continuous real time, which we call the time represent itself. And it's really important that, therefore, since there is no clock here, the dynamics of the system should match the dynamics time constants of the signal that you are feeding with. So if you want to recognize speech or recognize the gesture, we need to match time constants of the circuits to this external signal. To do that, we actually really slow down the silicon with having time constants between, I think, like 10 and 100 milliseconds. In return, it will also give us high bandwidth and reduce power consumption. So for the next couple of slides, I'm going to show you how we are building these circuits that is implemented on DYNAP-se to both match the time constant of the signals that are coming and also to process. So every analog neuromorphic chip that we develop at Institute of Neuroinformatics works at the subthreshold regime, where the drain source current shows exponential dependence on the gate source voltage of the transistor. And these currents are really low, as you can see here, nanoamperes and picoamperes regime. So from here, you can directly guess why these circuits are actually a bit noisy, because slight variance in the voltage that you apply to the threshold may give you like sometimes order of difference in the current that you are observing. But nevertheless, you can see that how this exponential dependence is also reflected in the ion channels of voltage-dependent ion channels in the neuronal membrane, like sodium and potassium. It's exactly the same exponential behavior. So the main building block of our circuits are DPI, differential pair integrator circuit. I'm not going to analyze the circuit here, but if you are if you apply this translinear principle across these loops shown with the blue, you will end up with the equation here. And this is a first order nonlinear differential equation, which you cannot solve explicitly, but you can do some assumptions. And under this large input current, larger than the time constant bias, you can end up with this approximated first order linear differential equation. So why this is important circuit? Why this is like one of the critical parts? Because it's a low pass filter with adjustable gain and time constant. By changing the time constant of this circuitry, we can really tune the time constant of our circuits and match to the incoming signal. So we are going to use this circuit both in our synapses and also in neural circuits in order to match the external time constants. So this is a synapse circuit that implements slow temporal dynamics. So whenever a spike comes, the weight current proportional to the weight bias discharges the cap here and causing the decay time constant controlled by this v tau. And on the right side, you can see with using different the biases, you can have different temporal dynamics here. These are exactly matching with the real physiological EPSP data. So this is the last schematic that I'm going to show. It's a schematic of neuron that implements adaptive exponential integrate and fire circuitry in DYNAP-se. It essentially has 4 different functional blocks. The blue block here implements the neuron's leak conductance. Purple block implements additional low-pass filter that integrate output spikes to later on use as a feedback current, which is responsible for spike frequency adaptation. This gray third block basically implements the event generation and the amplifier for positive feedback. Basically, it's a modeling the sodium ion. And this last brown block basically resets the neuron and implements a refractory period, keeping neuron at the resting state during the refractory period. So here we have more or less 10 different parameters per neuron that we can tune. And all blocks together, all the biases set properly, this neuron is capable of describing non-neuronal patterns like adapting, bursting, fast spiking, tonic spiking. And you can see here on the right how it can emulate actually the real data measured from a single neuron. So basically, it can really match the membrane, the characteristics, and you can see the bursting behavior here, for example. And there's a really old joke at Twitter that I've seen lately that single neurons can solve Hodgkin-Huxley differential equations. Our neurons, silicon neurons, can solve this adaptive exponential integrate and fire just as well. So what's inside DYNAP-se? DYNAP-se 1 comes with a blue box here. And again, it's important to mention here that DYNAP-se 1 is a small prototype chip. Initially built to explore the principles of communication of protocols across multiple cores and chips with hierarchical routing scheme. It's designed at 2014, and it's a small board actually. And inside this board, we have 4 different DYNAP chips, and each chip here shown has 4 different cores. You can see 4 different cores here, and each core has 256 neurons. So in total, with this box, you are going to get 496 neurons. Each neuron can have 64 fan-in and 4K fan-out. There are 4 configurable synapse types, which corresponds to NMDA, AMPA, GABA-A, and GABA-B type synapses. So you can tune the time constants or the weights of these synapses using computer. One limitation here is that we have single bias generator per core. So you have 256 neurons in the core, and you are going to use exactly the same biases for 256 neurons. Routing is done with high performance hierarchical scheme that is actually described in the original DYNAP-se paper. Events emitted by a single neuron contains destination of the target neuron address. And when event reaches the target core, it broadcasted to all synapses in the core. If the synapse has been programmed to look at this address, it will be activated. So we are using USB 2 for communicating with the DYNAP-se with computer. It also has the FPGA on board, which we are using usually to generate external virtual spikes to feed to the chips, or you can use this FPGA to really implement learning algorithms, like different online fast adaptation dynamics for your chip. And again, it has also the AR interface, which helps us to connect this neuromorphic processor. This is a processor, right? This to connect this one to event-based sensors like DVS or cochlea, silicon cochlea. So it can directly do the computation part when you feed it with the spikes. It has 16 analog monitors. So you have one monitor per core. With these analog monitors, you can reroute the membrane potentials to analog monitors and watch it real time. Actually, in the exercise, we are going to do that. So this chip is designed with 180 nanometer auto technology, but it's still a bit still you can see how power efficient it is. It's using 260 picojoule with 1.3 volt IO supply. So how we are going to program the DYNAP-se one? We are going to connect it with USB to computer. And we are going to use this Cortex control library that Dimitri is going to show you in a minute. I think he's going to explain this. This is a lot better. But basically, we can watch the raster plot, live raster plot of the chip for every single neuron here. And we can tune the biases here with this graphical user interface of Cortex control. It's not only limited with the graphical user interface. We can also create the RPIC server and using the Python API to basically configure every single bias on the chip with every the configuration between synapses and neurons, connection configurations. So this is not as really high level as PyTorch, but it's very similar to Brain2 simulator. Actually, the Cortex Control API is very similar to the simulation tool that we are going to use in the next 2 hours. So if you get really a sense of how the API works in the simulator, it's really similar with this Cortex Control used to control the chip. One question that we are getting constantly is, can we directly map our PyTorch models or TensorFlow models directly to the DYNAP-se? Not automatically at the moment. It's not automatically, but people are working on this at the Institute of Neuroinformatics. They are working on how to map artificial neural networks trained with backpropagation to spiking neural networks, or spiking neural networks implemented with any learning local learning algorithm to directly to DYNAP-se, considering the architecture, the graphic, the computational graphics that your neural network implements, and compare it with the constraints that the chip has. So I think I can give the floor to Dimitri.